Let's find the area under the graph of a polynomial.
So let's integrate from 0 to 1 the function x to the 4th dx.
To solve this problem, I can use the fundamental theorem of calculus.
So the first step is to find an antiderivative for x to the 4th. Well, what's an antiderivative just for x to the n, right, as long as n isn't minus 1? An antiderivative for this is x to the n plus 1 over n plus 1 plus c. So for this specific problem, right, what's an antiderivative for x to the 4th? Well, it'll be x to the 5th over 5 plus some constant c.
And it doesn't matter which antiderivative I pick.
So just to emphasize that point, let's be a little bit ridiculous and pick my antiderivative that I'm calling big F to be x to the 5th over 5 plus 17, right? And this really is an antiderivative for x to the 4th, because if I differentiate this function, I get the derivative of x to the 5th over 5, which is 5x to the 4th over 5, plus the derivative of 17, which is 0, and 5x to the 4th over 5 is just x to the 4th. So I really have found an antiderivative for x to the 4th. Right here, it's x to the 5th over 5 plus 17.
Now I apply the fundamental theorem.
So the fundamental theorem tells me that to integrate from 0 to 1, the function x to the 4th is the same as evaluating an antiderivative for x to the 4th at 1 and subtracting that antiderivative evaluated at 0. In this case, my chosen antiderivative is this function, so I plug in 1, and I get 1 to the 5th over 5 plus 17, minus what I get when I plug in 0, which is 0 to the 5th over 5 plus 17, and 1/5 plus 17 minus 17, well, this is just 1/5.
I can really see this fact.
So here's a graph of the function y equals x to the 4th, and what we just saw is that the integral from 0 to 1 of x to the 4th dx is 1/5. So there must be 1/5 of a square unit of area underneath this graph.
Let me get out my scissors.
Well, here's a rectangle, and the width of this rectangle is 1, and the height of this rectangle is 1/5. So this rectangle contains 1/5 of a square unit of area, and that's the same as the area under this graph. So let me cut this rectangle a bit. I'll shove that piece under there, and I've got this leftover piece, which I guess I have to do something with. Maybe I'll turn it over. Maybe I'll cut off this piece here. I'll put that there. I'll grip this there and sort of shove that in there, and there'll be a little bit up there. I mean, it's not great, the job that I did here, but it's at least believable that there's 1/5 of a square unit of area underneath this graph.
Admittedly, this particular case, the area under the graph of x to a power, this particular case was known to Fermat before Newton. And yet, what we're really selling here isn't the answer to a particular problem. It's a general technique for approaching these area problems. If you want to find the area under a graph of a function, instead of trying to do it by hand, you can apply the fundamental theorem of calculus and reduce it to an anti-differentiation problem, which hopefully is easier. This is an example of the way in which mathematics is a democratizing force. Problems that at one time would have been only accessible to the geniuses on Earth are now accessible to everybody, right? At one time in history, you would have had to have been the smartest person on Earth in order to calculate the area of some curved object. And yet now, armed with the fundamental theorem of calculus, we can all take part in these area calculations.